Good morning, everybody. Only a few of us here. I'm going to send a reminder and I'm also going to set up a bit, okay? I'm here. Good morning, everybody. All right, I'm here. I still didn't send the notice, but how's everybody today? I have my new setup. I have my new iPad, my new laptop, and my microphone is the same one, but it appears last week there was a serious sound problem that I didn't recognize or nobody mentioned because it was just a loud, the mic was set too loud. I don't know exactly what was happening, but and let me know if the sound is bad, if it's weak or if it's too strong, and I'll adjust it. Just sending a notice that we're live streaming now, and get yourself organized. We're going to review what remains to be explained about Unit 2 GDS, and then get into the normal distribution because I want to have it on the test next week, so we need to get started. Okay. So, I asked you to prepare the back-to-back stem and leaf plot. How many of you need some time to do that? Or some instructions on how to do that? And what you have to do is create a single stem that they share. You have to decide that now before you begin if you're going to do a split stem, like it is for Ruth, or a single, a regular stem and leaf going by 10. I'm going to choose this one, going by 10, because this drawing is enough to show me the features I want to see. Okay, and this one has a regular pattern, so if I condense it, it's not going to disappear. It'll just be amplified a bit. All right, so I'm going to use 0, 1, 2, 3, 4, 5, and I have to go all the way to 6. On this side, I'm going to put Maris, and on this side, I'm going to put Ruth. These are going to be their leaves here. Again. Okay, so I'm going to simply copy from this side. Sorry, from this side, I'm going to copy what I have there over here. Okay, so that's the stem and leaf sketch for Maris. Now going the other way for Ruth, just have to be careful that the values need to go to the left. So it means that the number line will run backwards. All right, so we are in the sample problem. What do you mean if you put the leaf inverted? If I reverse these, you mean? Is that what you're saying? So I want to put on here Maris, and see Maris will start here, right? Because it starts in the 20s. So 22, and then the next one is 25. So I'm going to include that here. You see, so I'm going this way in order increasing from left to right, and that will be for the 20s. So for the 30s, it's 34. They have to be aligned, and 35. For the 40s, it's 41 and 41, and then we have 6, 6, 6, 7, 9, and 45. That's all of them. So then we get to 50, 54, 54, and 59, and finally 60. There you go. So there is my back-to-back stem and leaf plot. Yeah, if you reverse them, it's okay. It's just you'll see what the difference is and why I did it this way. But it's not wrong, as long as you did things going, left to right. That's fine. You can put. These should be straight lines. I found out about the ruler last time. Okay, so I can make a line. Ugh, that didn't work, did it? You see, and it helps me make a line. You should be doing this on your own. I'm killing some time here. Okay. So what do we see? We begin with the shape, right? We have to smooth out the shape. And now if I want to smooth this one, it's pretty clear. I can go like this. So again, when I smooth, I'm saying, I believe if I had more data or the entire population, it will still have this pattern. Obviously, there'll be more figures or more values underneath. If I made a histogram with those extra, all those values, I think the shape would be pretty much like this. And for me, that is symmetric. What do you think? For Maris, the shape, now this is the thing, if you put Maris on the other side, you just got to be careful, because now I'm going to interpret this. Let's pull it out so we can look at it. Let's pull out this, and oh, it didn't all come. That wasn't good. Let's undo. Did I miss something? Try that again. Why is it doing that? All right, and then I'm going to flip it. I always wanted to do this. And now again. All right, so that would be the shape on the horizontal. And you notice if I do it, because I had Maris over here, because I had Maris on the right, the number line works from left to right. Did I just say? Yeah, this is right to left. This is left to right. I think I was saying it backwards before. Sorry. So this is, now if I was to smooth this out, I believe, when I smooth this out, I believe that the pattern will remain like this, that most of the observations will be together, spread out, and then you'll have just a few, just that one observation as an outlier. That's what I think. At least an outlier I need to verify. So we say this is skewed to the right because it's skewed in the direction of the few observation, the extreme value. So this one is going to be called skewed to the right. Now you can still call it skewed to the right if you did it the other way, but you have to recognize that the number line is backwards if you had put Maris over here. I'll call it right skewed. Okay. So that's the first point. Then we go through the second and third, because we see, 1 minute. Somehow putting that line there divided the data. So weird. All right. It divided my text that I printed. Okay. What next? Well, depending on this shape, determines the what statistics to compute, right? So because this one is symmetric, we need the mean and standard deviation for center and spread. So mean for center and standard deviation for spread. And for today's class, you should have watched all my videos, and we'll talk about which ones you didn't watch. This is kind of a review that I'm going to do right now, okay? That I'm doing right now. Let's see if I can. Yeah, everything is split up. So I'm going to erase this. Not giving up. Oh, it's all uneven now. Oh my goodness. All right. We're going to say the mean and standard deviation for Mayors and for Ruth, sorry, and for Mayors it's going to be the median, and for the shape, spread, it's going to be the 5-number summary and the IQR all of this because of the shape. You can also mention the range of values. You can mention the range in here and here. So these are the things we're going to calculate. Now I have all the results of this analysis, or this the 5 features in the notes for the sample problems. Let's do them on Excel. So some students let me know they didn't have the calculator yet, or I like to do this in the calculator and Excel, on the calculator that I chose. So if you have a different calculator, figure out how to use it, or you can watch a YouTube video, that probably be available, or just use Excel. So let's make the calculations and then we'll finish the other 2 features and then summarize, right? Any questions so far? Okay, so let's go into my calculator, and I want to use stat mode. So to activate the stat mode, I hit second data. I am going to be able to enter my data through this worksheet, okay, using this worksheet. So let's begin with, we're going to use this to calculate the mean. So for Ruth, the values were 22, enter, and then you scroll down. The second letter, Y, is like a second variable. We're not going to use 2 variable statistics right now. We're just talking about 1 variable. So we're going to continue with the arrows to go to the next one. Now enter 25. You put the number first, enter, and then arrow down. And then down again to skip over the second variable. Then 34, enter, and 2 down. 35, enter, 2 down. 41, enter, 2 down. 41, enter. Well, I guess I could have used, no, I have to do it like that, sorry. And then 46, there's 3 46s. So 46, enter, down. 46, enter, down. Oh, sorry, I did that wrong. Now I have to go back, right? So I'm going to go back, fix my mistake. So it was 41, and then 41, and then 46, and 46, I put it in the wrong place. This should be a 1. Enter down. So then the next one is 46. And this is a 1. And then 46. Down, down. 47. Down, down. 49. Down, down. 54. 54. 59. And 60. Any questions? Now I'm going to ask for the results. So we hit second stat. Actually, no, wait. First, I should go back to the data and make sure it's correct. So 22, and then 25, and then 34, and 35, and 41, 2 of those, and then 46, 3 of those, and then 47, and 49, and 2 54s, 59, and 60. Now, second stat gives you this. Okay, let's see. To show you the list of numbers. Okay, I'll just go through them again. Manuel? So let's look at them again. So 22. I mean, I could put the list on here. It's let me think about it. I have to open another thing. Anyway, so 22, 25, 34, 35, 241s, 346, 47, 49. Are you with me? Then 2 54s, a 59, and a 60. Okay, make sure everything's in there. I'm going to... You should have your notes in front of you. You really should have your notes printed in front of you, or maybe in another window. Okay, you're okay? So then I say second stat, and here are, what does LIN stand for? Does anybody know? Anyone guess? It stands for linear. Linear. Okay, so we're going to use this for linear regression. For now, we don't need all the information. We get n is 15, telling us we entered 15 values. Here's the mean. X bar is the mean, universal symbol for mean. So write it down, 43.93 repeating. And then next one is SX. SX is 11.247. Okay, and then there's this one, sigma x, which is 10.866. If we round it. I'm just going to round these, to 11, and they're both 11s, aren't they? And the other one is 44. Okay, so the mean is like 44. The standard deviation, SX, is 11. And the standard deviation, sigma x, is also 11 if you round it. So what's the difference between these two? Which one is higher? Which one is higher? Right, so Manuel recognizes that this one is based on dividing by n minus 1, so it's higher than this one that's dividing by n, gets a bigger number, is lower. That's very important. I'm going to talk about that in a second. Now what you get next are all the stats for the y variable, but we didn't enter anything in y, so there's nothing there. And then you get the estimates of A and B for the line, and there's no other information, and I get an error because there was only one variable. So all right, so let's talk about this. So we got x was I'm going to do these in blue. So x bar was equal to 43.9, but we just rounded to 44, right? Because it's hits, it's home runs, so those are whole numbers. And for the standard deviation Sx, or we can just say S because there's only one variable. We don't have to distinguish. It's 11.24, which we also, or 25, which we also round to 11. Whereas sigma gave us 10.8. They're very close. This also rounds to 11. The difference is, though, that S will always be larger, okay? The formula, so I'm hoping you saw my videos where I explain how S is calculated. If not, please watch it today. I can't do everything that I want in the lecture. You have to watch those edited videos. So this is S, whereas sigma I think it's too low. This is driving me crazy. Why it separates my stuff. So this formula is for sigma. Okay, so what's the difference between this and this? This is the sample standard deviation, and this is the population standard deviation. Now, your calculator doesn't know what you've got, all right? You have to enter the data. It gives you two measures, but this is a statistic and this is a parameter. That's why I teach you at the beginning about them, so you distinguish between them. This is the sample standard deviation, and this is the population standard deviation. And our data we're going to treat as a sample So we use this one. We don't use that one. Although in this case, the numbers rounded are they're about the same thing anyways, but in general, they're not the same number. It's not the same number. It's just because I rounded it. I made them the same. That made them the same. So what's the difference? In the sample, I average the deviation squared from the mean. So this I call an average. If you watch the video, I explain that. Even though I'm not dividing, I'm not summing, this symbol means sum. I'm not summing, I'm not dividing by the total number of observations, I'm dividing by one less. And I explained that in the video, I believe. Can anybody tell me how I explained that, or what you understood why we divide here by n-1, whereas here I am using a capital N for the population size. Okay, so n-1 represents degrees of freedom. That Manuel's right, but what does that mean? Why does that happen? What happened to freedom? Why did freedom go down? Why did the degrees of freedom go down? I'll wait for you. So every observation, every value in a sample, or every value of data introduces a degree of freedom. So you have in the sample, you have n degrees of freedom. In the population, you have capital N degrees of freedom. What happens when you go from the parameter, which we might never be able to calculate this, right? We might not have all the observations, but theoretically, I need the deviations from the real mean, not the sample mean. In using the sample mean, I am connecting all the observations, but that's not all of the data, right? That's not all the population data. So by doing that, I lose a degree of freedom or degree of randomness. Now it turns out in practical terms what happened is if you do this, if you calculate the standard deviation, it could be, there's a tendency for bias of the results. There's a tendency for it to be off. So if you calculate S with n here instead of n-1, and you do this for many samples, so this is how statistics works empirically. You can test these theories, all right? So we can create a population, we can sample repeatedly from it, and from each sample calculate a standard deviation, and then look at the average of those standard deviations, and it turns out that the average standard deviation doesn't hit the sigma. It should. That's it should on average it should end up being the actual population standard deviation for the created population, but it doesn't. So you can show this all theoretically, which I won't do, but to adjust we want standard deviation to represent the spread or the range of the data. We want to be able to use it to capture how spread out the numbers are. So it turns out that it's better if you want to kind of cast a net, you want a wider net, right? So to make it wider, dividing by a number smaller, the S ends up a little higher. So S will always be bigger than sigma. Okay, S will always be bigger than sigma. And we're going to use it. So how do we use this now? Any questions so far? I'm going to show you how to use mean and standard deviation. Actually, no, let's do this in Excel first, and then I'll do it. So let's do this in Excel, because I said I would show you in Excel. And then we'll do the interpretation. So let's get Excel. So entering values. This is not very useful. I'm going to go to the other keyboard. Oh, it's slower. Okay. So I want to calculate the mean. Uh-oh, my keyboard has changed languages, I think. Oh no. Okay, I'll go back to the other one. So now I want to enter equals, and I want to write mean or average. No, it's not going to give me, I would say average. For Excel, average. Now writing average, it asks for the values. So what you can do is, oops, I just lost it. So I'll do that again. Equals average and most of you should know how to do this, right? So what you want to do is you want to highlight I'm using the Excel on iPad. It's a little bit different. And I want to erase all this. And enter. There it is, 44.57. That's too high. Did I enter a value wrong? I missed something. I missed 35. Oh, I missed a value. There it is. Okay, good. So that's the average or the mean. Now for the standard deviation, we're going to say equals, and You want the sample standard deviation. So I think it's just going to be this one. But let me check. I'm saying think because there's two, and I usually use this one. But there's also that one with .s. Let's see if they give you the same number. Okay, that looks fine. So that's the standard deviation. And you see I'll be dropping off saying sample, but I'll put it right here just to remind you. That that's for the sample. All right. And there's that other value, that other measure. What happened to my keyboard? Equals. If you say standard, you see there's a standard deviation .s. Let's see if that gives you the same thing. Yeah, it's the same thing. So that's standard deviation .s. So it distinguishes between sample and population. So that'll give you the same thing. I don't know. I don't know. I never saw this before. My nephew showed me this. I'd have to look it up. I was just working with him on something. And he's like, oh, do I use this for standard deviation? I said, no, just use the standard deviation, STDF, DV. But I guess they have it in there to distinguish it from population standard deviation, right? This one will give you that's exactly what we got. This is ST for the sigma. Okay? All right, so that's it. Any questions about that? Average and standard deviation will give you the right answer for the standard. Okay. Yeah, it's pretty, I don't know, Excel introduced this other, I've never seen that before until the other day my nephew showed me. But I guess it's just to distinguish between the sample and the parameter, the sample and the population. Okay. All right, back to work. So now what? What do we do with these values? I'm just going to use 11. Maybe I shouldn't use 11. So the rule in my notes is for final answers, use just use 2 decimals more than the actual values. Now these values had no decimal. What just happened? These values have no decimal places, right? So I should just keep 2 decimal places in my results. So let's just do that. So I'm going to use the X bar. I'm going to use no, I'll just use 44 and 11. It's going to be messy. Okay, so I'm going to use 44 and 11. Just remember it's from S that I'm using. And I'm going to write down the one standard deviation from the mean interval. So the interval of one standard deviation from the mean. So I'm going to do that on another page. So make an interval with 11 plus 44 and 11 minus 44. Now this is 1 standard deviation from the mean. Now in principle, 1 standard deviation from the mean, this is how you use standard deviation, gives you like most of the data is within 1 standard deviation, the majority. So let's go back. So this is for any kind of distribution. It should be the case, okay? So let's go back and check how many observations are between negative 33 and 55. Count them. It's almost all of them, right? Because there are 15 and there's just 2 that are not. So that is how many? That's 13 divided by 15%. So this captures 13 out of 15. So this is like the net that we're casting. How many do we catch? Okay, got 87% within 1 standard deviation from the mean. So that's what a standard deviation can give you. So most of the hits are between negative 33, which is really just 0, and 55. Did I do this wrong? I just did it backwards. You guys didn't stop me. I did it backwards. This is why I didn't want to do another page. Okay, no. Do it again. Do it again. Live streaming problems. Okay, do it again. Get a chance. You're probably perplexed. What the heck did she do? 11 and 40. I did it again. Why do I want to do that? 44 and 11. I'm not sure. All right, there. I did have a good sleep. All right, do that one yourself. I don't know. So do that one yourself. What do you get? Makes more sense now. It still should be most of the data. What's the range? So the range will be between 33 and 55. So now let's go count. Between 33 and 55, how many observations? So 33 and 55 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? That's a 11. So right. So that ends up being 11 out of 15, or 73. Okay, so that's how we do it. We show a range of values. So most of the data, most of his hits are between 33 and 55. Okay, so it's high. It's high. These are high number of hits. So I'm going to put it here. And you can go one more time because we're going to capture everything within 2 standard deviations. What about 2 standard deviations? What would be the interval for 2 standard deviations? So the higher the standard deviation, the more spread out the data, and this is how we use it. And we did this, the reason we're doing this, and we didn't do this before, was because this data, these data are symmetric. So take a screenshot. Okay, so because it's symmetric, I can talk about going around the mean, right, in an equal distance. So that's how it's spread out. So that's a full answer for standard deviation, for spread. This is the one here. This one here. What? All right, questions? Now for Maris, you need to calculate the 5-number summary, the IQR, and mention the range. And both of them you can say the range, right? The range of this data is between, for Ruth, the range is between 22 and 60. And you can calculate that. So it's a spread of 38. That's another way that you should summarize the data. Actually, I'll do those in blue. Okay. Now, to compare it to Maris, so this is why we're using the back-to-back stem and leaf plot to compare the two distributions. And you see that Ruth peaks higher than Maris. And I don't even call this a peak. I refer to this as relatively flat. In the range of values for Maris, it's much more spread out. And we want to mention that too, so that's why I mentioned the range here. You're going from 8 to 61, that's much more spread out. So Gerardo's asking to be an outlier. To be an outlier, for us, I should mention it now. Well, it's one of the things that we got to get to here. This is killing me. The separation. Okay, what I'm going to do is just move things over maybe. Not good. Okay, so what I'm just going to do is okay, I'm going to mention about there's no outliers, right, for Ruth, because so when there's no data outside of 3 standard deviations, there's no outliers. Everything has been separated. I'm trying to reattach things. Everything is separate. That was not a good move. I thought I'd separate everything and then put it back. All right, so what I'm going to do is, I guess I'm going to write up here. For Maris, we want to calculate the median and the 5-number summary and the IQR, right? Now, I've done all of this already, but I think I even have it in the notes. But let's do it on another page, and then I'll put the results here. So the nice thing is all the data is in order. The data are in order. And there are 10 observations. So the middle now the middle you can really see, but in general, when you have a large data set, just to identify the middle, you would use this technique, right? So you find 1, 2, 3, 4, 5.5. So between these two, Nicole is asking about the blank page. I don't know what you're referring to, what I wrote. Oh, did I write it 60 here? Yeah, 66. No. That was 2 standard deviations from the mean. This is the range. This is the range. This is the minimum to the maximum. That's what range means, Nicole. The other page was 2 standard deviations from the mean. They just look like similar numbers, but they're different concepts. So the full range is captured in 2 standard deviations from the mean. So the median will be between these two, and it's not going to be one of them. So the median doesn't use all of the values like the mean does. It just uses these 2 values, or no values at all. It's just the middle observation, but in this case I have to calculate it. It's 24.5. Now that divides the data into 2 halves. So to find the first quarter, I find the middle of each of the halves. So this ends up being Q1, and I did do this last class, and for another data set, and this is Q3, because the median is Q2. So what you would do if you had a large data set is you would calculate the middle of the first half. So you would find the middle by doing the calculation n plus 1 over 2, but now you use the n of 5 because that's the first half. And then also for the middle of the second half, is Q3. Again, n plus 1 over 2 of the second half, that's 5 plus 1 over 2, or the third observation in the second half. Nicole, are you okay with that, what I explained? So I have my values, 14, 24.5, and 33. And the median was not one of the values, but it's the median. It's the middle value. So I'm going to put that here in blue. Okay, those are them. That's a 5-number summary. The range of values, okay, so the IQR would be the IQR is 19. And the range of values from the minimum to the maximum, and the calculated range is 53. I'm going to just circle it all. Okay, so this is the kind of information you give for the 5 numbers, for the spread for Maris, and you see the range is not double, but significantly broader for Maris. And we have a way of, so this was the way of looking at the data spread out, right, with the standard deviations from the mean. But here for 5-number summary, this is the way I demonstrate how spread out it is. And I'm going to use this to look for outliers. So what I'm going to do is take this now to another page. I'm going to just not bother with the graph. Just you have to remember that graph. I'll take this with me. Hopefully, I lost it. Let's see. I think I got it all. And continue. Okay, so I'm going to continue with the description because now we have to do the other 2 features. And for the 4th, it is the gaps and outliers. Now we already determined there are no outliers. We'll go back and look at the drawing to see the gaps. So let's see, are there any gaps in Ruth? Nope. And Maris, yes. So no gaps, no outliers. So it's revealing how steady and predictable that distribution is, okay? And for Maris, there are gaps. In the 40s and the 50s. And for outliers, let's check. Remember how to check for outliers. The main question is 61 an outlier. Okay, I'm going to take a break. You're going to check that for me. I'm going to take 5 minutes and you're going to check that, okay? Yes, Pablo's right. So the n is the number of observations in the first half. So there's 5. The number of observations in the second half, 5. So how would you know that? You just you literally divide your data. Your median divides the data in half, so use that to determine what's on the left and what's on the right. All right, so I'm leaving you for 5 minutes to tell me whether 61 is an outlier. Okay, I'm back. Okay. So let's see. To test for an outlier, you need to check are there any observations so what you're going to do is take your 5-number summary. Actually, I'm gonna pull up my notes. I think I do this in the notes. Let's see. Let me verify. Okay, so here I have a nice drawing. So here I've presented the 5-number summary, and essentially what we want to do is we want to take this, I want to take this distance here, which is 19, which is calculated range between the 3rd and the 1st quarter. And what we want to do is add that same range so I want to add that same range here and a half. So I want to make this bigger. I want to make it 19 So it's 19 plus a half of 19. And half of 19 is 9.5, right? Or you do that by 1.5 times 19. Which is 28.5. So actually it's not very good scale, but okay. So this and a half of it, you spread it out. You spread it out by adding 33 plus 1.5 times IQR, which equals 33 plus 28.5, and you see that gives you 61.5, right? Just covering 61. Or is that 63? All right, I've exaggerated my graphic here, but the point is it captures. It's a net that's cast again. So we use like a spread to catch, and we see, oh, it's in there. So nope, 61 turns out not to be a statistical outlier, however strange it may be. Take a screenshot. Oh, opened the wrong one. We can still refer to it as a, like, technically, okay, in statistical analysis, we will not identify it as an outlier, but it is an extreme value, and we would call it a suspected outlier until we test it. So the answer is no. Okay, any questions? Before I continue, I want to make a point about Excel and percentiles. So we know, the way I've shown you how to calculate the quartiles is a very specific way, different from what some statistical software packages do. So it just turns out, as much as we can standardize so many things, standardizing percentiles has not been achieved. Okay, so if you actually put this in Excel, you don't get 14. However, well, I argue to you that it is 14. You'll get 14 and a half. And it's just because of a different technique used. So what they do instead is they'll use a percentile. Now, percentile, to figure out a percentile, what you need to do is and I do mention this in the notes. Everything I talk about I mention in the notes, or at least in the annotated note. But you might have missed it. So let's say I want the 50th percentile Okay, so you want the 50th percentile if you have 10 observations. So the 50th percentile is the position where you have 50% of the observations at or below it. Now that particular definition, at or below, is sometimes changed to just below. So it's not standardized. It's not wrong if you do it, if you use Excel, okay? But it'll help you understand if your answer is slightly different than somebody else got. They might have been using a statistical software that had a different definition. So 0.5 of 10 is 0.5 times 10, which is equal to the fifth observation. So the fifth observation would be the percentile of 10, but that's not what we did, right? The fifth observation would have been 23. We didn't do that. We did it this way, which I'm pretty convinced I prefer this way to doing it. So you'll have a different answer. So depending on your assumptions and the technique you use, you have a slightly different answer. Okay, so using this technique, it's not wrong. You can see as well for other percentiles it'll be the same. Now in Excel you have a function for percentiles. So you'll see. Let's check in Excel with our data set. Did I put this data set in Excel? No, I didn't. So let's put this data set. Yeah, Gerardo. It's a standard way statisticians use. And again, different statisticians could use different ways, but I haven't run into arguments. Either all of the ways are agreed upon, they're all equally good for different reasons. Nobody really mentions this because it can confuse people. Why would that be so different? It just is. So wait, I'm going to put the data for Maris. Let's see how Excel does it. So what I'll do with Excel is I'll get the 5-number summary, like the Q1, Q2, and Q3. There's different functions in here. So it's just that it's not predictable what I'm going to get because it depends on the formulas they're using. So if I want, let's just say median. Let's see what we get. Oh. Okay, so we got the same value. So we did get the median here. If we did percentiles, let's see. Percentile. So let's do that. Percentile, and we'll click the array. Let's make sure I got the right numbers in there. Oops. And then you have to tell what percentile. So I think you have to put 0.25. 0.25. Oh no, I want 50.5. It worked. So the percentile is right. So now let's do quartiles. So the first quarter that I got, my method was 14, right? Let's get the first quartile. So this is median. This is the 50th percentile. Trying to make it, it's not a 50%, but it's 50th percentile. It's autocorrect. Do it this way. And let's do the 25th percentile. Let's calculate 25th percentile. Well, my Excel on my computer didn't do this, so let's see if this will work. So if I want percentile again, I pick the same array. Jeez. What did I do wrong? And then 25. There you see, 14.5. So the answers will not be what you get. They'll be slightly different. We got 14, but this gives us 14.5. So just in this class, that you probably won't run into it. It's just I'm telling you now in case you get frustrated because you're doing everything in Excel and your answers are slightly different than mine. Okay. It wouldn't matter if you're doing like a paper test, but with multiple choice, you might get slightly different answers. So just be aware. Just be aware. I won't intentionally trick you. And that's not my intention, but you might get confused in studying. So let's see why that happened. They got 14.5 for the 25th percentile. So if we did the 25th percentile, so 25th percentile in 10 observations. So they must do some interpolation, because the 25th percentile of 10 is equal to the 2.5th observation. And so they must take, so 2.5, right? So it's still very strange, because that's 2.5 would be between here. So I don't know what they're doing in Excel, really. It's been 20 years. They still haven't standardized things in my teaching career. I'm kind of surprised. But in general, in this class, you will see this result. In life, it's okay. 14.5. Just be clear about when you write a paper or a report, you have to say what software you used. That's how you resolve. This is how you create transparency. Software or equipment. Because science should be replicatable. Is that the word? Replicable? Replicatable. Other people should be able to, with the same data and the same resources, get the same answers. Questions? Hope that didn't confuse you. Okay, yeah, if you took the first half, that's a good approach, Omar. If you take the first half of data, you'll get the same answer, because it looks like it's calculating the median right. So that's a good point. Now, it's troubleshooting. Very good. So if you took this data here for the first half, it should work. Genius. Okay, so somebody asked, I'm asked, why are we just checking for Q3? So the fact is, we see in our problem, we see that there is an outlier on the right. So that's why we check for it to be statistical outlier on the right. We don't have to check both sides. Okay, but if it was on the left, you would use the Q1 minus 1.5 times IQR. All right, all we have left are the peaks. And I don't know, I think I didn't do the peaks for the other problem we did the other day. I thought, I wonder if we finished that. So peaks are, in the first distribution, clearly there's a peak in the modal class of 40s, the 40s. And for Maris, there's no clear defined peak. I would say there are no peaks, okay? So if you have a clearly defined one modal class peak, you would say that's a peak. But this is just no clear peak. It's rather flat. So you would say there's a peak. Oh, I wrote 40 to 50 here. Let me specify this is 49 and this is 59. Sorry, I'm going back. So the gaps and outliers, the gap for Maris would be 40 to 49 and 50 to 59. And yeah, the peak would be 40 to 49 here, and you say no clear peaks. The distribution is flat. Okay, that's it. So that's Maris and Ruth. In conclusion, you can write a conclusion. Once you've systematically listed the 5 features, you write a conclusion. And what was my conclusion in the data? I posted here. You can say a bunch of things, but this is what I chose to say. Ruth's distribution reports a consistent record, having an average 44 home run hits, give or take 11. So that's how we refer to the plus or minus a season. Maris's distribution reveals that he has 25 home run hits a season, so I rounded up the 24.5 to 25. Where 50% of the time he is hitting anywhere in the interquartile range of 15 to 33 home runs. As Ruth's average of hits per season is higher than this range, so I'm going to use the interquartile range for a skewed distribution to refer to the regular portion of the distribution. So since Ruth's average number of hits is above this range, we'll say Ruth is clearly the better baseball hitter. Got it? So that's that. So for the spending data, I also have that summary that we talked about. There are a couple of other data sets in here, and I go through them in the videos, or I use the data in the videos. I use Newcomb's data to make histogram. I discuss the reason why we use the select data set and come up with this histogram here. I just want to say something about Newcomb's data, and then let's see in the notes if there's any questions you have. You have the annotated notes, so you should be able to answer or see the answers to most of the questions there. I'm pretty sure all the questions. So this is the data set here. Here are the data for the different problems. And we've taken care of this one, and that leaves Newcomb's and this discussion about the meets. For Newcomb's data is trying to the collection of data was used to estimate the speed of light, and this was done in a very particular way using distance and flashing a light from one place to another and recording at the other place the time that the light was shone. So at both ends, the time was recorded, and then the difference in time was used with the distance to estimate the speed of light. So because light travels so fast, they use a mirror to reflect, to catch the reflection that was sent, where the light was sent from an origin. And then the speed is so fast, nanoseconds were used as to estimate the time. So the time is what the dot is here. The time different from 24,000 and some nanoseconds. So this is the slight variation in those recordings, which can be because of variation in the speed of light. Okay, for whatever affects the speed of light, it creates this slight variation. So when you look at the numbers, they're rather similar. They're mostly between 20 and 40, right? They're mostly between 20 and 40, except for a few lower values. So we begin with data. You always start with data preparation, right? You plot the data and look at it. When you plot this data and look at it, depending on the plot, so there was here's the stem and leaf plot of Newcomb's data and the histogram, and clearly these are outliers here. Are they statistical outliers? Yes. If you test them, you'll find out, because most of the data is very tight, around 30-ish, looks like. This histogram, I teach you how to make it in a video. Please watch that. And before we continue, we have to determine, since we do have outliers, will we keep them, or is there a rationale to eliminate them, because they will affect our computations, and it makes a natural phenomenon very inconsistent. Okay, and we don't want that. So let's look at the data in a different way. Here's a view of the data by order of measurement. So this plot is a different plot. This is a time plot recording the order at which the measure was taken. So most of the data, as explained before, varies between 20 and 40 about, except for these two. Now look, these two were early on in the experiment. They were early on in the experiment. What does that tell us? It's not random, right? They were early on, systematically biasing early on measures. So can we explain that and justify eliminating these? Well, we could say these were measurement error. These were measurement error, something in the instrumentation or familiarization, in the process of familiarizing themselves with this experiment, some errors were made. Maybe on one end, the person tripped and shone the light. He passed the light and recorded the timing wrong, or in the other end something happened. So there's something in actually capturing the measurement that went wrong, that didn't go wrong later. So I justify dropping these as outliers due to measurement error, and I see no reason, since most of the data are pretty regular, that I can drop these. Now, in general, you have to justify dropping data and make a record, keep a record of what you did and why you did, because it's going to dramatically affect your estimates for the mean and standard deviation. Well, you're going to calculate mean and standard deviation, but because the data are skewed, you're going to use the median and the 5-number summary and the IQR instead. So that's what I wanted to say about Newcomb's data. Some of the coding here, this is all the coding used to make these graphs in Stata. You don't have Stata probably, nor do you have access to it. But my intention is to get Stata software in our computer labs so that I can start teaching with Stata. All right, so that's Newcomb's data. Watch the video on making that histogram. And so I have a lot of videos that explain the notes. Oops. Go through all of them. I don't know what else to tell you. Oops. I guess that's overloaded. This shouldn't be happening. I guess I have to delete something. Let's try it like this. It's having trouble reading that file. Okay. All right, so videos on all these topics, how to recognize skewness, using the 5-number summary for skewed distribution, the decision rule, and then I have some exercises here, and then this discussion of box plots. And everything should be solved in the notes. Does anybody have any questions? I want to go to the normal distribution. No questions? So read through these notes, go through the videos, and let me know if you have any, if there's still something that is missing from the explanations I provide in the edited videos. And otherwise, I'm going to introduce normal distribution and then leave you for those videos. There's also this discussion here. All of this, these are for two, so then I talk about two variables at a same time and how to draw, how to visualize them, and some immediate kind of comments you can make about two variables at a time. But the videos are already produced, so have a look at those. And I'm going to start with the normal distribution. I mentioned here I did describe how you can recognize skewness from a box plot. And I'm just mentioning here, you can also get a calculation of skewness out of Excel. And Excel will use this formula that looks somewhat like the standard deviation, some sort of like, but it's not the standard deviation. So this is a measure of skewness, and the higher the value, the more skewed the value. If it's negative, it's left skewed. If it's positive, it's right skewed. Okay? So you can look into that. But I'm not going to test you on that formula or anything. It's just to let you know what Excel, the black box of software, is giving you. All right, so we spent time talking about, first we talked about collecting data and different types of data. And I settled on telling you we're going to focus, this course is going to be focused on quantitative data. Quantitative data that is continuous and discrete, but right now we're going to focus on continuous data, and then in Unit 4 we get to discrete data and discrete variables. Because Unit 2 and Unit 3 uses continuous data. So as well, we talked about skewed distributions, and although I've taught you how to interpret and report on skewed distributions, how to test outliers, all these features of skewed distributions, I want to now focus on symmetric. So we're going to work with symmetric distributions, more regular and predictable, because we want to be able to make those predictions. So relative frequency histograms, if you haven't watched the video, make sure you do, about creating this sort of a histogram. So it's, as opposed to a stem and leaf plot that shows you the values that are inside, it just notes how many there are in each class. All right? We have percentage of observations on this axis as opposed to number of observations in a regular frequency histogram. And so since this represents the percentage of observations, we interpret that all of these bars, if you were to total the height of all the bars, you would have 100%. Of the data. Now, just like any other distribution graph, I will smooth out the distribution with the understanding that if I had all the data, I believe it would have this general pattern. Let's see what I can do about that. I didn't want to do that. I just wanted to watch me struggle with this. There we go. All right. No, that didn't work. All right, so I smooth it out, and I would say that the area under the curve is known as the density curve. has 100% of the data below it. All right? Because I'm treating this density curve as though it represents the whole population, I'm going to call the middle mu. Because it's continuous, it's going to run from negative infinity to infinity. And I'm going to name the variable that's plotted on this axis x. So uppercase x represents the random variable, and the lowercase x will represent a specific value. So for instance, let's say there's a little x here. What do we call x? And I'll use colors. I'll say the blue x. So what is blue x? What do we call blue x? I'll change this color. It's the mean, right? It's the median. And it's in the modal class. What are some other names for x? What are some other names for x? What about the 50th percentile? Okay, so these mean the same thing, median and 50th percentile, but now calling it 50th percentile, I'm going to show you how we express that in statistical notation. What I can say is that 50% of the observations lie to the left of x, right? So the bars total 50% on the left of x, the blue x. So I could write that as 5, 0, or 0, 0, or however many zeros I want. It's 50%. I also want to write that as the proportion of observations or percentage of observations, or because I'm referring to this density curve as representative of my population, I can also say probability, or the chance is 50% that the variable x will be less than blue x. Those are all the same meaning. So I'm going to write it down, and then I'm going to write it like this, or write it like this. They're all the same. Or write it like this. Okay, those are all the same thing. And P is for percentage, proportion, Also frequency or relative frequency. Sometimes people just say frequency. They're not very kind to people who are learning. Relative frequency. I'm going to run out of space. So percentage proportion, relative frequency, or because of the notion of the density curve and the relative frequency histogram, this representing the population, I can talk about the chance or the probability. So all those words mean P. Or P means all those things. Everybody good? So what I'm showing you is that area to the left of a value, that value is a percentile. Okay, so we call X, blue X, 50th percentile. What about I'm going to use X star. So X star, let's use X star. And I'm going to put it here. And I'm going to tell you in advance that the area to the left of X star is 1%. So those are all the same thing, right? 1%, 0.0100, 0.01. They're all the same thing. So how would I write that in statistical notation? No comments? So we would write the proportion of values under the curve smaller than X star is 0.01. Or 1%. Or 0.0100. And we would call, what do we call, we call this the 50th percentile. What do we call X star? Other way around, Pablo. The other way around. Not 99th, but... area to the left under the curve is the percentile, is the percentage relevant for the percentile. Okay, so this is called the first percentile. What if I'm here? And I tell you that all of those bars sum to 25%. What is X star star? What are the name? What could we call X star star, and how could we express it in statistical notation? Ah, very good. Right. You guys are getting it. It's the third quartile, not the third percentile, but it'll be the third quartile for sure. Or you could see it as the top quartile, the first quarter, top first quarter. So you can look at it in two ways, right? This position marks 2 points of view. You can think about the area to the left, you can think of the area to the right. So we can have lots of names for this. You need to know all of them. So it should be also the 75th percentile. So it's on the left, that gives it the name 75th percentile. On the right, we say it's the top 25th percentile. So anytime you point right, you refer to the top, not percentile. Percentile refers to the area to the left. Okay, so let's write it in statistical notation. We can write it a couple of ways. We could have written the other ones a couple of ways too, but I didn't get into it yet. So x, the area under the curve, greater than x star star is 25. That's what I told you. Or I can write it like that. And that's the same, well, not the same, but it's the same value has a different perspective. The area to the left of it is 75, or the third quartile. Or let me just write it because there's not too much room. I'll say Q3. I could also say it's it marks the top Q1, doesn't it? It's the position where 25% are above it. So I'm doing this again, or I'm looking at it from both perspectives. So are you guys good with this so far? I have one more thing to do with this chart. So I haven't shown you standard deviation at all here. All I'm done here is talked about percentiles. So the interpretation, we can interpret positions along the number line here and translate them relative to where they are in terms of the observations. Okay, last one. I'm going to make some space for myself. And say, what about, now you're going to tell me how much area is in here. How much area, how many observations, in other words, what's the percentage, what's the proportion, what's the relative frequency, and what's the probability of being between X and X double star. So the big black X refers to the area under the curve. So you say the chance or the probability or the percentage of observations under the curve that are less than X double star is 75%. So the big X represents the curve, the variable, the distribution. Yes, so between here and here, very good, is 25% chance. Okay, so I can put this up here so you can see this is, well, I don't know why. Okay, so so this is 75, all of this is 75, all of this is 50, so in between here must be 25, right? So let's write that up. So the probability, now I'm going to write this up, always thinking of the number line left to right, the numbers get higher, right? Correct? So between, the smaller one is the X, and the bigger one is X double star, and I put the big black X here between, and I write like this. That means between. So the area between, or the probability of falling between X and X star, double star, is equal to 25%. These are all the same number. Questions? So if I want to say between, I put the arrows, like that. And they always go small to big. So I can calculate, or I can interpret area to the left area to the right, and area between as percentage or chance of seeing observations. So this represents, like all these other examples, let's say this represents spending. Let's say this was spending in a cafe. Okay, so this is the distribution of spending of customers entering a cafe throughout the day. And these were, this is the amount of money people spend. They can spend very little, they can spend very much, and they could spend, most of them spend somewhere around the average. Some spend a little bit more than the average, just as many spend a little less, and just as many spend a lot as spend a little. So this is an example of symmetric distribution and how we use the relative frequency histogram to interpret the possibility of seeing spending, certain amounts of spending. So 25% chance of people spending more than this amount. Okay? All right. So area to the left is percentile. Area to the right, we call it the top percentile. So let me do one more example about the top. So if you want to know about the top 1% or the top, let's do the top 1%. If that was 1%, and I just say that that's, I'll just make it X triple star, what the heck. Okay, so X triple star, then X triple star is in the top 1%, which is important, right? If these were grades or spenders, these are the top 1%. Spenders spend more than this amount. That's percentile. All right. Any questions? See, something's got missed. I'm gonna put this. What am I to do? Okay, I can hold it. See if I can group them. All right, I put it back in the group. I'm learning as I'm going. All right, somehow I did it. All right, so I put them back together. All right. Oh. All right, so the area under the density curve is 100%. The area under the density curve at any one particular value, however, is 0. What am I talking about? The area only exists, density only exists between a range of values. So I talked about less than and greater than and between, but we don't, because it's a continuous distribution, the chance of being just at exactly one value and trying to find the probability of that, we say is 0. Okay, it's not interpretable. And I use an example to demonstrate. Remember that between any two values, there's infinitely many values, right? Because it's continuous variable or continuous values. So if I tried to find that value at a point, so let's say just a blue X, X. So let's say that, let's make that X and say I want to know the probability of the variable being exactly X. What's the chance of that? The answer is 0. All right, you can ask me later if that's confusing for you. All right, so I'll just make some point that the pth percentile is the value such that p% of the area under the curve lies to the left of it. And then I just drew it again to make any other examples if you need them. All right, now, so this is just recapping what I've said so far. Because density curves are idealized, we imagine that we have all information possible in the variable when we are smoothing out the underlying relative frequency histogram. When density curves are symmetric, we have a special name for the center or mean of the distribution. We use mu, right? That's the Greek letter for m, or mean in our case. M for mean. And there's a special name for the spread, or the standard deviation. It's sigma, the Greek letter S for standard deviation. Now, though these were calculated from a sample, when we do what we're going to be doing, we treat those measures as like substitutes for the population mean and standard deviation. So that's why I'm renaming them. And because it's a symmetric distribution, I name them particularly mean and standard deviation, because those are the parameters for a symmetric distribution. Okay, that doesn't mean if someone gives you a mean and standard deviation that the distribution is symmetric. However, you always need a graph, right? You can't just say if someone gives you a mean and standard deviation that you assume the distribution is symmetric. Anybody can calculate these values for any data set. It doesn't mean it's correct interpretation of the data. So all of those properties are true of symmetric distributions. The special case of density curves that are normal have one additional property. And that property is known as the 68, 95, 99.7% rule. So what is that about? Remembering for symmetric distributions we use the mean and the standard deviation, which I'm going to rename as mu and s, and I'm going to check, or I can calculate one standard deviation from the mean and know that most of the observations should lie within one standard deviation of the mean. And within 2 standard deviation of the mean, I could get all the data. Well, in particular, this is, even though in the exercise that we did today, we didn't get that 68% of the observations lie in one standard deviation from the mean. We got, what did we get, 73? It was kind of close, but it was 73. But within 2 standard deviations, we got all of the data. Well, that's not the case. With the normal distribution, it's spread out in a particular way where there's 95% between 2 standard deviations, and within 3, there's 99.7. It's done this way to ensure that there are outliers. So it allows for very extreme values considered outliers with, outside of 3 standard deviations from the mean. How many outliers? What's the percentage of outliers? Very good. 0.3. Right. 0.3%. So it's, you both were right, I guess. So it's 0.3% outliers. Which you could also write as that. Okay. So let's draw it. Let's draw it here. And then it's 11:30. So we're going to spend 50 minutes on this, and then I'm going to refer you to all the notes. The videos I already made. So you need to review those videos to understand the rest of the notes. And then next class we're going to get together, and after you've studied all week, right? And I'll do some review. If it's fine with you, I'll just do 1.5 hour review and then give the test for 1.5 hours, or I can spend the whole 3 hours doing the review and then give the test after class. I'm not sure how we can vote on that. I guess you should just let me know, so we'll know that day. So the question of the day is, you can email me if you have a problem with the decision. Be 10:30. How are we going to decide this? Okay, so in the chat, tell me which one you want. I had already said I was going to put it at 10:30, but let's see if anyone is opposed to leaving it at 12. Let's ask that question. Okay, so if you're opposed to a 12 p.m. test, write me. Write me an email or a text, or you can mention it here. But that's going to be, I think that's the best. We can have the 3-hour class just to do review and answer your questions. And I can give you the test, and the test is 1.5 hours, and it's going to be multiple choice, just like the quizzes in in Moodle. Okay, so a lot of people want 10:30 anyways. Get done with it. Okay. Well, you can write me if you have any debate. So since there's already 3 people who want 10:30, 4 people that want 10:30, I'm going to probably stick with 10:30. So write me about your situation. All right, so let's see. I want to draw this now. Oops. The way I'm going to draw this is I'm going to, so next week then we'll spend the first half hour, so 1.5 hour review plus 1.5 hours for the test. Okay? Now, maybe 1 or 2 people just show up for the review, and the other ones can just come, be studying, and then just arrive or open up Moodle to see the test at 10:30. So to study for the test, you have all the midterms questions. You can get examples of the types of questions there are. It's just everything. The midterms have also regression on them, so just skip those questions. But those midterms would prepare you for the other type of questions, so study those. Okay? Regression will be on the next test. Okay, so what we're going to do is, well, that's not very good. Let's see. I'm going to put mu in the middle, and I'm going to put the peak there. And what I'm going to do is I'm going to draw a curve down. So it's going to be a concave function. I'm not able to do what I want to do. There we go. So what I'm trying to do here is match them up. Okay, they're not going to match up. There we go. All right, so there you go. Now they're off center, so I will just redraw this. So the idea is that this is concave around the mean here. This is not good. This is all off center. I have to move the whole thing. Not going along with me. Okay, so no. All right, so basically that's what I want to do. I want it to be the same. I want it to be identical around the mean, all right? And then that will happen up until 1 standard deviation from the mean. So on both sides. So this distance should be the same as this distance. So I'm doing the give or take, or plus or minus. And then the function turns up like this. It goes convex. So this is an inflection point. Like that. And what you get is, so you've probably learned this before if you've learned stats. If you haven't, you've never seen this before. But there's a histogram under there, and the histogram is just like what we did before. But in here specifically, within 1 standard deviation are 68% of the bars, 68% of the observations. Within 2 standard deviations, so I have to move an equal distance this way. That's not equals it. So this spreads out like this. within 2 standard deviations. Now within 2 standard deviations, are 95% of the observations. Okay, so the area in between here is going to be 95%. And finally, the area between here and here, so the area under the curve or the bars under here will total 99.7%, leaving some outliers here. So 0.15% of the observations here and 0.15% on the other side. Or we can write 0.0015 on 0015. Okay, now if you think about the data that we analyze, Maris and Ruth, we looked at Maris's data. Maris's was not a normal distribution, was it? Sorry, not Maris. Ruth's was not a normal distribution, because we found for Ruth that 100% of the data was in 1 standard deviation of the mean, so that wasn't normal. So normal doesn't mean all the time it happens. Normal is the name given to a distribution that is spread out like this, and many phenomena are approximately normal. So we use the normal distribution to make predictions about what to expect. All right? So that's just, in general, that's the distribution, but I can give you some values and you can draw, or you can depict the distribution, and then you can answer questions about what to expect from that distribution. Before we go, I just want to say something. So the idea is that the area under the curve and the distribution of the area under the curve is the same from normal distribution to normal. So if you have 2 distributions that are normal, if I told you that's normal and I told you that this is normal, or approximately, and I told you that I'll call this A and I'll call this B. This would be mu plus sigma A, right? And this would be mu minus sigma A. This area in here, the bars, should be 68% of the observations. So what does that mean about sigma B? It means sigma B must be bigger than sigma A to make it more spread out, first of all. So maybe this would be sigma B. Everybody, I hope you're okay with my notation. not meant to confuse you. It's meant to help explain things. So for this to be normal, if these are both normal, then this would have to also be 68%. Sigma B would have to be bigger than sigma A for this drawing to make sense. I mean, for this to be what it is here. And the other thing is, to get this drawing, if I didn't have the drawing, I'd have to explain to you that B is flatter than A. So it turns out that this actually has to be down as well. This has to be pushed down to spread things out. Okay, so this is like clay, or you can think about Jello in a mold. If you have the same amount of Jello in different shapes, still 68% of the mold should be in 1 standard deviation from the mean in either case. So the peak for B should be down further than A's peak. All right, so really everything is in the notes, I mean in the videos, so you have to work through it. And let me know if you have any questions. We can meet. The tests will be very basic. I think even to send you to the midterms, they're much more challenging. If I was to take a screenshot so I can go to Moodle. This looks very different than I'm used to. I forgot my password. Oh, I think I just typed it in wrong. Okay. So what you have are the normal distribution review modules. Some are longer, but they're like 5-minute videos. I added these up at once, a few hours in here to go through the notes. It'll take you longer to go step by step. And then you have practice assignments, you have these quizzes, and in the next section, if you skip over regression, you get tests. Okay, so these are for practice. If you have time, you can go through some of these, and they're multiple choice. That's all I can give you on Moodle. And you can see the kinds of exercises. And I'd say probably more challenging than I'll give you, but they'll be good practice if you have time. Like I said, I don't mean to kill you with the test. I mean to just make sure, we're all on the same page, and you have an incentive to study, and you have some feedback about how you're doing before the course continues. All right, so we'll say the test is at 10:30 on next Saturday, and it'll be for 1.5 hours. Any other questions? So it will be Unit 1 and Unit 2 completely. All of Unit 1 and all of Unit 2. All 3 modules. So next class, I will focus on the normal distribution for 1.5 hours, and then I'm going to give you the test. So it's not what we covered till now, it's what's online. So if you have any questions, you can let me know, we can meet, and we can do exercises together. We can either do it in YouTube, or we can just do it in Zoom or something. Figure it out. Okay, so have a happy Valentine's Day weekend. And I'll stay on. If you have any questions, I'll stay on for a couple of minutes. Otherwise, have a great weekend and holiday on Monday. I hope you get to enjoy your holiday. Bye for now.